So, Maths for Non-Programmers Who Program. That's a bit of a crazy title. So, what's that all about? This is a talk for people who are video game developers and the video game developers who don't actually consider themselves video game programmers. So, this could be people who write scripts in Unity or Unreal for blueprints, and I'll mostly be focusing on Unreal for blueprints, but it could be anything, even your own game engine. Or whatever, but it's basically for people who wouldn't call themselves a programmer, but they are actually programming it, whether they like it or not. And it's for those who want to learn some basics, mainly about a little bit of 2D and 3D math that will help you go a long way, so you can do better gameplay. Maybe you can write better graphics or shaders, and like I said, you can do this in 2D or 3D. So I'll be showing you examples in Unreal Engine, but these techniques can be applied anywhere, and because I'm showing you the theory, you could even write your own math library with this. So it doesn't really matter what the engine is, but I'll show you the Unreal Engine's examples. You'll find calls, the kind of calls I'm showing, you'll find those in most game engines. So the motivation for this is this quote from Charles Dickens, which is, "A very little key will open a very heavy door." So I'm only going to show you a very small amount of maths, but this maths is used everywhere in everything. So if you know how to do this and you realize the power of it, you'll get through 70-80% of the problems, and you only need to know a couple of things to do it. So what are we going to show? Like I said, very simple but useful vector math. We're going to cover in detail on the actual math that's involved in there, demystification of the math that's in the math library functions in the game engine, and you'll realize it's actually not that complicated. Definition of vectors and points, vector length and normalization, what the vector dot product is and how you use it, and some examples in 1D and 2D. And I'm going to tell you that the stuff I'm showing in 2D works in 3D as well, but it's pretty hard to draw in 3D on a slide. So most of the examples will be in 2D, and show you the math notation as well. So you could write this thing down when you're actually trying to work out the problem before you calculate it. So vectors and points. So what is a vector? A vector is something that has a direction and a magnitude. So that's a direction and a length you could think about, or a direction and a size. So there's an example of a bunch of vectors, and you can see they're all different lengths and different sizes. They go in different directions and they're different sizes. So two vectors are defined to be the same if they have the same direction and magnitude. So from that diagram on the right, I can see that vectors u and v in the middle one, the big ones, they're the same size and they're going in the same direction, so they are the same vector. I've drawn them in different places just to show you that it doesn't matter about that. What matters is their size and their direction. I can see that vector A is going in the same direction as V, but it's not the same length, so that's not the same vector. And vector W is the same length as A, but it's going in a different direction, so that's not the same vector. So only U and V are the same in that diagram. So what about a point? Well, a point is something that has a location and no size or direction. So that kind of seems like the opposite of a vector, is that a vector had a direction and magnitude, but a point doesn't have a direction and it doesn't have a magnitude. So it's kind of the opposite of a vector, although there they are. We kind of represent them in the same way, but there's a bunch of points that I've represented just as dots on this graph. And all those points are different. They're all in different locations. They're all different. So 2 points are only the same if they share the exact same location. And that's it. So if you're in Unreal, for example, it only has vectors. If you've used Blueprint, there are only vectors in there, which is a bit weird. You've got this make vector thing, and there's make vector 3D, make vector 2D. So if I'm saying that vectors and points are different, how can we only have vector? So a vector is represented in the computer as a location that has some distance from the origin on each axis. So that kind of makes sense. That's what we're saying. It's, you move along in some direction and up in some other, and you get a vector. But then a point is represented in the computer as a location that is some distance from the origin on each axis. So that seems a bit weird as well, because it seems like they're basically the same thing from this point of view. So we can actually use the same data structure to represent both. Unreal does this, and it's called vector for the 3D one and vector 2D for the 2D one, and I think there's vector 4D as well for a 4D one. I think Unity has a vector 3, which is their version of it, and they don't believe that either of those engines has a point, a separate point class, because a lot of the operations that you do on one, you can do on another. And as we see in the next slide, vectors and points are related, so we kind of want to interchange them and just store them in the same type. We just call it vector for convenience, but keep in mind that a vector and a point are different, but we represent them inside that vector structure. So if we have 2 points, we can turn them into a vector. So you can see there on the right, we've got 2 points, P and Q. If I do Q minus P, I get a vector U, so I get a vector from P to Q. So any 2 points, I can turn them into a vector by doing that. And similarly, we can turn a vector and a point back into a point. So if I do a vector plus P, I can turn it back into Q. So you can see that I can go from having 2 points to getting a vector, and then I can take a vector on one of those points and get back the other point. And you can see that the bottom equation is basically, if I just add P to both sides of the top equation, I get the bottom equation. So the two are related, and I can interchangeably go between them. So we store those in the same data structure. Like I said, the points and vectors, we just store them in a data structure called vector. And you can see on the right there that we've got 3 inputs to that is point in box. And point is a point, box origin is a point, and box extent is a vector, but they're all given inputs. Those yellow inputs are all vectors. So we just use the same data structure to represent both, but it's up to you as a developer to know that what that thing is, whether you're thinking about it as a point or a vector, or you're interchangeably moving between the two in whatever you're doing. And yeah, you can think about a point as being a vector from the origin if you want. So you can already almost think about a point as being a vector in any other circumstance. So you can see why we don't bother with 2 data structures. It would just get a bit weird, and it would just make the code more complicated. But mathematically, they are different. As you can see, I can do different things with them. So as an example, we've got this, we're going to do a one-dimensional problem, and it's going to be a drag race, and it's not that kind of drag race. These are going to be cars. So I've got this little diagram set up, and there's A and B there. I'm going to represent cars, and F is the finish line. So given these 2 cars, A and B, traveling in the positive direction in 1 dimension, so I'm going to do this example in 1 dimension, which one is winning the race to the finish line, F? Now, if you just look at it, it's pretty obvious that B is winning this race by an absolute country mile. But how do we represent that mathematically? So we can think about A and B as, the points A and B as a magnitude and direction from the 0 point. So we can think about them as vectors from the 0 point, which we're calling our start. And even though A and B are points in 1D, yeah, we're treating them as vectors. So can we now do some primary school maths that just solves this problem? So for each car, we're going to calculate the length from the start and subtract that from the finish point, and the smallest result is the car that's closest to the finish. So in effect, we're going to be doing what we did in our other diagram, is that we've got 2 points and we're going to create a vector from them, and the shortest vector is going to be the shortest distance to the finish line, and that'll be the car that's winning. So if we take the finish line minus A, so that's our 2 points, we get 4 minus 1 is 3. So we can think about that car A as having a 3 vector to the finish line. And the same thing with B, we do F minus B, gives us 4 minus 3, which is 1. So there's like a 1 vector going to the finish line for car B. So car B is winning because the smallest one is the one that's winning. And it all seems totally trivial, that's just so simple, it's not even worth thinking about. But you can see that we're already in 1 dimension. We're solving a problem, and we're kind of thinking about them as vectors, even though they've just basically only got 1 dimension to them. So problem is harder in 2D. The 1D case was easy to find the length from the 0 point because we just read the number off the graph, and it was very easy. In 2D, we can't just add together the components of the vector to get the length. So car A in this diagram is at 3 across and 4 up. We can't just add 3 and 4. That gives us 7. So that vector V is not 7 long. It's clearly smaller than that. So that we can't do that. There was only 2 points that the car could be. If we said it was at 3, it was 3 length our vector. It could be at 3 or -3. And in 1D, there was only 2 places, but in 2D, there's an infinite number of places it could be. So 2D's definitely got harder in that case. Yes, there's an infinite number of points or a given distance from the origin, so that's definitely harder. And what about, even though I've drawn this finish line in green here, what about if the finish line isn't horizontal? What about if it's just all over the place? How do we calculate which car's winning then? So we can clearly see again on the diagram that in this case A is winning. But where do we start? So the first thing we want to know is how do we get the lengths of these vectors, the vectors to A and the vectors to B. So it's pretty easy. We just use the Pythagoras theorem to get the length of the vector. So Pythagoras theorem, if you don't remember from high school, is a squared plus b squared equals c squared. So given that triangle with sides a and b, if I take side a, square it, take side b, square it, add that together, I get the length of side c squared. And Unreal has a bunch of functions to do that. They call it vector length and vector length squared. So this also, works in 3D and 2D. It works in as many dimensions as you can throw at it. So the math to do that here at the bottom is basically we take the components of we can take the components of the vector and square them and then add them all together. And this v with the bars next to it, it just is a mathematical way of writing the length of the vector v. So vx times vx plus vy times vy plus vz times vz is the length of v squared. And if we square root both sides, we can just get the length of v. And you can see that's why a lot of engines and Unreal, one of them, can give you a function for the vector length squared, because you can see that you've got to calculate the vector length squared before you can get the actual vector length, because you've got to do an extra square root on that to calculate it. And the reason why you might want vector length squared is because the square root operation is reasonably expensive in computing terms. It's way more expensive than all those other operations put together. So if you can avoid doing it, you probably should. You can't always do that, but sometimes if you're comparing two lengths, you could just compare the squared lengths instead of the length, and then you don't have to. You can save yourself multiple square root operations. So it's well worth considering using the squared length if it's available for your particular problem. So given that, can we solve the race winner in 2D? Now we can use Pythagoras theorem to find the length of the vectors. So for car A, that's just 3 along and 4 up. So 3 squared plus 4 squared gives us the length of v squared. That's 25. And if we square root that, it's 5. So the length of v is 5 units. And that's how you get that in 2D. And for car B, it's 4 squared times 3 squared. That's the length of u squared. Square root that, we get 25 as well. And so the length of u is also 5. So both car A and B have travelled the same distance, but they've travelled that distance in different directions. So that's our definition of these vectors, that the two vectors are only the same if if they have the same direction and magnitude. These have the same magnitude, but not the same direction. So we clearly can't just take like the finish line at 5 up and subtract 5 from it, because we just get 0. So we'd get the same answer for both cars. So we can't just do that as it is. Both cars have travelled the same distance in different directions, and we can't just measure that. So can we solve the race winner in 2D now? No. We need to redefine the problem of who is winning this race as the shortest distance to the finish line, but in the direction of the finish line. So we didn't really have enough information before. We need more information to define this problem. And remember, when we did the 1D problem, we said we were going in the positive direction. So we knew the direction of the finish line. So I'm going to define the direction of the finish line as this normal vector. I'm putting it as an n up there. And that normal vector is a 1 unit vector, and it's a vector of any direction you want, but the length is always 1. So I'm defining that as in this case, as a 1 unit vector, and I'm defining the distance to the finish line from the origin as this d in the direction of this normal. So I'm getting these two extra things. And then we're going to use something called the vector dot product to determine the distance from the finish line for both of the cars. So I'm not defining the dot product yet, but we'll get to that. So the dot product takes two vectors as input and returns a scalar value, and a scalar value is just a number or a float. And it can be used to project one vector onto another vector, and that's a really important thing to realize about what the dot product does. Is it allows us to project vectors, and once we can project vectors, we can recast problems into other dimensions, and we can think about it as casting the shadow that one vector will cast onto another vector. We can work that kind of thing out. So essentially, we're going to turn this 2D problem back into 1D to solve it, and because we can solve the problem in 1D, we did that in one of the first slides. But our 2D problem was much harder, but we can solve 1D. So if we turn the 2D problem back into 1D, we could solve it in 1D. So it seems like cheating, but that's what we're going to do. So what we're going to do is we're going to project our vectors for our cars. We're going to treat car A and B as a vector from the origin. We're going to project them onto a vector that is like the distance, the vector coming out from the finish line. So that's why we needed that direction of the finish line. And then once we know the length of the finish line, we can subtract the lengths of the other two vectors that we projected, and then we can work out which one's further. So you can see on this diagram, this is a slightly different one, but you can see that we project A and we project B onto these lines towards the finish line. We can see that A is winning in this case, and it does make sense because you can see that A is closer to the finish line if you just look at it. So the finish line, it's got a unit length vector that points away from the finishing direction, and we have a distance from the origin. So we need those two pieces of information to do this. And that's what I said. We'll treat the locations of the cars as vectors, project them onto the line, and then find the lengths in one dimension. So totally cheating. We're going to do it in one dimension. And if you do this same problem, I've done this in 2D, but if you do this in 3D, it comes out the same. Like this problem extends totally to 3D, and if you wanted to go to 4D or 5D or be crazy, it would work in those dimensions as well. So the math to project the vectors is pretty simple. Unreal provides a couple of functions to help you with that. It's project vector onto vector, which under the hood is using the dot product, and project a vector onto a normal, or vector project onto normal. So two slightly different things, but they basically do the same one depending on whether you have a unit normalized vector, which is a vector of length 1. So the math for that, project vector onto vector, is reasonably simple. So we've got this dot product, which is the v dot w. So that's our dot product that we've not properly defined yet, and we divide that by this w with the bars. That's the length of w squared, and then we multiply that by v. So if v is that top vector on project vector onto vector, it would be a vector dot product with the two vectors, divide by the length of w squared, and then multiply by v. So that would project our vector onto another one. And if we do the same thing with the normal, it's just slightly simpler, because it's just the first vector multiplied by the dot product between the other two vectors. And the reason for that is if you look at the w bar, which is the length of w, and you square it, if that happens to be a unit vector, the length would be 1, and the square of 1 is 1. And if you divide anything by 1, you don't do anything to it. So they just give you a project vector onto normal because it's a simpler calculation, so it's faster. So a lot of these things you'll find when you look at these, there's always multiple versions of them that are just more performant if you happen to know something about the input data, which is what this one's doing. And however, this still requires a definition of what the dot product is, this v.w, which we haven't defined yet. So let's define that. There's a function there that Unreal gives you to dot product two vectors, and you can see that's exactly what I said, is that you get an input of two vectors, and it outputs that green is a float. So most textbooks that you read, or if you looked up the textbook or Wikipedia definition, will define it like this, which is, it's not a very nice definition, but it is a definition that's worth knowing. So we're defining the dot product between two vectors as the length of the vector v times the length of the vector w times the cosine of the angle theta between them. So that assumes that you are going to work in angles and all this kind of nonsense. And although this is a good definition to know, I don't really like this very much because it's got this notion of angle in there, and we really don't care about angles a lot of the time when we're doing the dot product. So we quite often use it without the notion of angles. So if we take this again, this is just what I said before. There's the definition of the dot product. That's what the lengths mean and the cosine of theta. The actual implementation, when you simplify it, in the computer is represented as this down here, which is you literally just take the components of each of the vectors, multiply them together, and then add the results. So you take the first vector's x and the second vector's x, you multiply those together. You take the first vector's y and the second vector's y, you multiply those together. The first vector's z and the second vector's z, you multiply those together. And then you add the whole lot up, and that is the result of your dot product. It's incredibly simple. It's really just a rearrangement of the Pythagoras theorem. So it's super quick, and it's super useful, and it's something that's so powerful, and it's used everywhere in shaders and collision detection and everything. So it's well worth knowing how this works. And it's mainly this property of being able to project one vector onto another, which seems to be one of the very useful features, especially if you're doing gameplay. So what can it do? The result of this defines how perpendicular two vectors are to each other. So you can tell if two vectors are in the same direction, opposite directions, or perpendicular. So it's not just like perpendicular or not. There's a whole grade of perpendicularity that you get out of this, which when you think about it is what the Pythagoras theorem was telling us is like how perpendicular stuff was. But now we've got this like gray area of how perpendicular they are. Allows us to project one vector onto another. That's incredibly useful, and allow to find the separation of two vectors and even find the angle between them if you needed it. But most of the time you'll find that you don't. And what kind of problems are we going to solve with this? Things like if you're doing AI and you want to steer a character, like if you want to know this thing's on my left or my right, how much is it on the left or right? How should I steer to it? Is this thing in front or behind me, and how much is it in front or behind me? Like, should I call this out if I'm rendering graphics? If I'm doing collision detection, maybe I can find out if I've got a point, is it inside a sphere or a circle? And same thing is like for culling or collision detection, like testing a point to see if it's in front of or behind a plane, which is almost what we did in the 2D examples with the cars, except it wasn't really a plane, it was a line in 2D, it would be a plane in 3D, but it's almost exactly the same math. So yeah, graphics, collision detection, gameplay, they're all super useful. So in the 2D example, we said that there was this 1 unit length vector that we defined for the finish line. What about if you don't have a unit length vector, but you want to get one? So that might be a thing you want to do quite often, like I want to get at this just pure direction vector. So Unreal has a bunch of functions to do this for you. They call it normalize. You can see there's the 3D ones at the top. And there's 3 lots of 2D ones, which has normalize and normalize safe, but the 3D one only normalizes safe, and we'll come to that, why there's a safe version and an unsafe version in a bit. But if we normalize a vector, it just gives us a vector in the same direction. It doesn't change the direction, but it does change the size, and the size is always 1. It's a very useful vector to have because it allows us to be able to go, like, take any vector, turn it back into a 1, and then go out from there at any distance we want. So we can get to any point in that distance by actually getting a unit vector. And you can see that if you needed to make one for your finish line, then you could make one using this normalize function. So to do that, it's really simple. To make a normalized vector, all we have to do is divide each of the components of the vector by the length of the vector. Now, we already know how to get the length of the vector because it was the Pythagoras theorem. So we get the length of the vector, and we take that length and divide each component individually by the length. So that's what this says here. This v hat is the notation for a normalized vector. So that's a vector v of length 1. We take the input v's x, we divide it by the length of v. The input v's y, divided by the length of b. And the input v's z, and divide it by the length of v. So that's sometimes, if we do that, sometimes referred to as a unit vector. So I'm calling it. Sometimes people will call it a direction vector because it represents purely a direction and not really a size anymore. It's just size 1. Or you might see it as a normal, which is like a normalized vector. So it's basically a vector in any direction you want, but it's only length 1. So it's really easy to calculate that. And if you are normalizing, that's the exact way that the computer will do it. So a few simplifications. That's the initial geometric version of the dot product, the cosine theta version. If v hat, that's the v is normalized, that kind of drops out. So it's just the result is just w, the length of w times the cosine of theta. And similarly, if w is normalized, then that drops out the other side because the length is just 1. So it's just cosine of theta times the length of v. And if they're both normalized, they both drop out the other side, so you just get the cosine of theta. So how do we create a unit vector from a vector in Unreal? We just take our input vector, we call normalize on it, and then we get our result. So what did that do under the hood? In this case, we had a 3, 4, 5 vector. We squared each of the components. Remember, this is just Pythagoras theorem. We take our square root of that. So we find the length of the vector 7.07. It's square root of 50 in this case. And then we take components 3, 4, 5. We divide them by the 707. And then we get out our new components for our new vector. And if we do this and we print out the result in Unreal, there you can see that my hand calculated version is almost exactly the Unreal version. So you can see that under the hood, Unreal is doing this calculation. And the reason for the tolerance is because there is one kind of like, you could call it a degenerate vector. And that would be what happens if you tried to normalize a vector that was all zeros. So if all the components of the vector were 0, and if you think about that's not our definition of a vector, because a vector has a direction and a magnitude. But if they're all zeros, then it has no direction, and so really it has no size as well, I suppose. So it's not really a vector if it's a 0, 0, 0. That's like, that can only really be a point. It can't be a vector. So if you put zeros into this, eventually you would get out a length of 0, and then this to try and calculate the normal, you try and divide by zeros with all the components. And I think if you did that with integer math, you'd get a division by 0 exception, and if you did it with floating point math, you'd probably get positive infinity or something like that. So Unreal has just got basically that safe version is detecting that if this vector has a length that's smaller than this tolerance, I think it might be squared length they're doing as well, then they just output you zeros from the normalized vector. So they can't normalize a vector that is 0 because it's not a vector. So that's okay. And then one more thing is just keep in mind this, if you're new at this, maybe this seems obvious, but maybe it doesn't, I don't know. But a 1, 1, 1 is not a unit vector. And you can test that by just putting all the components in, squaring them, take the square root, you'll see that it's a 1.73 length vector. So don't put a 1, 1, 1 or a 1, 1, 0 or a 1, 0, 1 vector in there and think that you're going to get a unit vector, because it's not. But you can always normalize any vector you've got and turn it into one. So there's your test to see that if you've got a unit vector or not. If you did have a 1 on one of the axis and not the other two, that is a unit vector though, because it's just one length in one of the axis. So just keep that in mind if you're putting together unit vectors. So that's pretty much it. That's all I really want to show you. I think you need to just, once you know all this, you can go out and start using the dot product and using vector projections to try and solve problems that you've got in 2D and 3D and trying to put them into like, you're basically casting them into this 1D space to solve them. So we learned that what I said at the start, the little keys can open big doors. This does a lot. The functions that I've shown you here and knowing the maths behind them really does a lot. The dot product, vector length and vector normalization, solve an absolute ton of problems. Recasting the problem from 3D or whatever into 1D can make very difficult problems possible. And most of the time, this is how you solve most of the problems. And although I've shown you the math behind them, most game engines will have functions that help you do these. So I think knowing how they work really does help you when you're calling them, because a lot of the time you'll be calling these. You might call functions that you don't need to because you've already got the answer. Or you might have an engine that doesn't have a particular function, like it doesn't have project vector onto vector for some reason, and you can write it yourself, or maybe you're doing it in some weird programming language that doesn't even have a math library. But now you can write these functions yourself, and you can get to these kind of answers yourself, and you can avoid doing unnecessary calculation, and you can solve a ton of problems and do more with very, very little. This is, like I said, this is really a cheat, because most programmers don't want you to know this, but this is how we solve virtually all of the problems. So I hope that helps the programmers out there who aren't programmers.